I want to start today with a question that feels, I don't know, almost a little insulting. Is it actually necessary to teach computers how to read?
It seems so simple.
It does. I mean, every kid learns to do it in primary school. So how hard can it possibly be? Why is there this entire field of science just dedicated to getting a machine to do what a first grader does before recess?
Well, that's the classic paradox of artificial intelligence, isn't it? The things that feel incredibly hard to us, like calculating pi to a billion digits or playing grandmaster chess,
Party for a computer.
trivial. But the things that feel effortless to us, like knowing that the word bank means the edge of a river and not a place for money just based on the context, that is just agonizingly difficult for a logic-based machine.
And that is exactly the source material we're digging into today. We're looking at foundations of computational linguistics and natural language processing.
And they don't pull any punches.
Not at all. Their verdict on whether we need to teach computers to read is, well, it's a three-part answer. Yes, it is absolutely essential. Yes, it is incredibly difficult. And yes, it is possible.
But barely, just barely.
Right, barely. So the whole mission for this deep dive is to figure out what it actually takes to bridge that gap. Because you have human communication on one side, which is methy, it's emotional, it's completely dependent on context,
And on the other, you have computer logic.
which is rigid, binary, and, frankly, a little bit stupid when it comes to any kind of nuance.
I think stupid is fair, or at least alien. The text makes this really profound point right at the start about the core conflict. Humans, you see, we invented language to talk to other humans.
Right.
When I say I'm hungry, I'm relying on the fact that you know what a stomach is, you know that feeling of emptiness, you have a concept of food.
I have a little simulation of you in my head. I know you're a person.
Exactly. But a computer, it's a creature of a totally different nature. It doesn't eat, it doesn't have a childhood, it has no fear. And yet, this whole field, intelligent automatic text processing, is about using our human emotional tool to exchange information with that alien.
So why even bother? If it's such a fundamental mismatch, why are we trying to force it? The source lays out this age of information argument, which, usually feels a bit cliche, but here they frame it as a problem of pure physics.
It's a supply and demand problem. We're just drowning in text. And the source gives two scenarios where human processing just, well, it completely breaks down. The first one is the secretary scenario.
This one really struck me as a pure efficiency argument.
It is. I mean, imagine you're in a business, you have to write a formal letter, maybe in a language you don't speak perfectly, or even in your own language, but you don't know all the obscure formal rules.
Which is most of us, let's be honest. My professional life depends on spell check.
And that's the point. The text argues it is just so much cheaper to teach a machine once how to format a document correctly than it is to try and retrain every single generation of humans to be perfect grammarians.
It's cheaper to build the tool than to fix the user.
Exactly. But the second scenario, the lifetime scenario, that's the one that really got me. It's this idea that to make a truly informed decision, let's say, predicting the global demand for coffee next year.
You'd have to read everything. Every report, every tweet, every shipping manifest.
And they calculate that physically it would take a single person 100 years of reading, 247, with no sleep, no food.
So automation isn't a luxury in that case. It's the only way it's even physically possible to do the task.
Precisely. If you want that kind of answer, you have to use the machine. And that, right there, is the science of computational linguistics.
Okay, but I think we need to draw a line here because, I use Microsoft Word to type, but I also use Notepad. Is everything that handles text considered linguistic software?
No, and that distinction is really the key. The source uses that exact Notepad example. If you type in English or Spanish or just complete gibberish into Notepad, it behaves exactly the same way.
It doesn't care.
It doesn't care. It just sees codes, not language. It's not, in their words, language dependent.
Whereas a spell checker?
A spell checker absolutely crashes and burns if you don't tell it what language it's looking at. You run an English spell check on a French document, and it just sees red everywhere. That dependency, plus the fact it relies on huge dictionaries and rule sets, that's what makes it linguistic.
Okay, so if we're going to build this software, we have to teach the computer what language is. And this is the part of the source material that just completely broke my brain. It starts with the most basic question. What is a word?
It sounds like a philosophical trick question.
It does. If you'd asked me 20 minutes ago, I'd have said, a word is the string of letters between two spaces. Simple.
And that is the perfect computer answer. But linguistically, that idea just falls apart almost immediately. The source has this great experiment with a single sentence in Spanish to prove it.
Let's do it. The sentence is, Yo devuelvo los libros el próximo mes, pero tú me devuelves el libro ahora.
Which just means I return the books next month, but you return the book to me now.
Simple enough. So if I'm a dumb computer just counting strings between the spaces, I get 1, 2, 3, 14 words.
14, that's your baseline count. 14 word occurrences. But just look a little closer. The word el, which means the yeah, it shows up twice.
Ah, okay. So if I'm only counting unique strings, I'm down to 13.
But are devuelvo, I return, and devuelve, you return, are they really two different words, or are they just different forms of the same verb?
They're both just the verb to return. And libros and libro. That's just plural and singular of the same noun, book.
Exactly. So if you group those together, you suddenly drop down to 11.
And hang on, if you want to get really precise, los is just the plural of el. So that gets us to 10.
And here's the killer. What about me and yo? They both refer to the first person, to I. Me is just the object form.
So conceptually, this sentence only has 9 distinct ideas. Wow, we started with 14 strings, but we only have 9 concepts.
And that is precisely why the term word is kind of useless to a scientist. It's just too vague. So the source introduces the exact terms we have to use to program this. You've got the word occurrence, the 14 raw strings.
Right.
You've got the word form, the 13 unique spellings. And then finally, the most important one, the lexem.
The lexem, that feels like the aha moment.
It is. The lexem is the abstract concept. The set of libros is one lexeme. The verb devolver, devuelvo, devuelves, and all its other forms, that's one lexem.
So for a computer to actually read, can't just count strings. It has to see the occurrence, match it to a word form, and then figure out which abstract lexem it belongs to.
And that whole messy process of mapping, that is computational linguistics.
It really feels like, well, it's like we're peeling an onion. You have the text you can see, but underneath it are all these different layers of structure.
The source describes it exactly like a stack in programming. At the very bottom, you have phonology, the actual sounds. Then morphology, which is what we just did, breaking words into their basic parts.
Then syntax.
How they fit together in a sentence. And then right at the top, you get semantics, which is, what does it all actually mean?
And what's so cool is that the structure, it isn't just for one language. It actually lets us connect different languages. This is where the source gets into comparative linguistics.
The family trees of language.
Right. I think most people have a vague idea that, Spanish and French are cousins and English and German are cousins. But the source makes it clear this isn't just trivia, it's a predictive tool.
It's all about pattern recognition. If a computer knows that a Spanish word ending in ixon almost always matches an English word ending in ixin.
Like revolution becomes revolution.
Exactly. Then it can start to make educated guesses about words it has never even seen before.
There was one example in there that I just loved because it feels like magic. The connection between the Spanish word agua and the French word eau.
They look nothing alike. A computer just comparing the letters AGUA and EAU would say they are completely unrelated.
But they're not.
Not at all. They both descend from the Latin word aqua. And there are established linguistic laws, these rules of phonology, that show how sounds decay over centuries.
So aqua becomes agua in Spanish.
And in French, the hard consonant sounds just fall away and the vowels shift until aqua becomes o. Because we know the original Latin, we know the rules of change, we can prove they're the same word.
That's amazing. It's like math for history. And speaking of math, the source brought up a name I'd never heard before. Yuri Morozov.
Oh, the man who deciphered the Mayan glyphs.
And he did it without a Rosetta Stone, didn't he?
He did it with pure statistics. This is what the book calls quantitative linguistics. Back in the 50s, everyone thought Mayan glyphs were just, symbolic pictures. But Morozov, he just looked at the frequency of the signs.
How often they appeared.
And he noticed that certain symbols appeared next to others in patterns that perfectly matched the statistical distribution of syllables in a spoken language.
So he basically moneyballed the entire Mayan language.
He really did. And that is exactly what our modern large language models do today. ChatGPT doesn't know what a word means. It just knows the statistical probability that the word happy will be followed by the word birthday. It is Morozov's method on a planetary scale.
But that's where the machines get into trouble, isn't it? Statistics are great for the average, but language isn't always average. It changes completely based on who you're talking to.
Sociolinguistics.
Right. Your work voice versus your, talking to your friend's voice.
And computers hate that. The source calls these sublanguages. A formal legal contract is essentially a different dialect from a text message. And if a machine tries to apply the rules of texting to a legal document,
You get a disaster. And it's not just social, it's geographical too. Dialectology. The book tells this great, sort of sad anecdote about Gabriel Garcia Marquez.
I love this story. So you have this Nobel laureate, a total master of the Spanish language. He goes to Cuba to teach a film class to students from all over Latin America.
Mexico, Argentina, Chile.
And he realizes he can't speak his own language naturally.
Because his Colombian Spanish isn't their Spanish.
Exactly. Every time he used a common word for, say, bus or cool or a hangover, half the class would just look at him blankly. He had to constantly filter his own vocabulary down to find the one universal Spanish word they would all understand.
And if a literary genius struggles with that, just imagine trying to write an algorithm that works for Spanish. Which one? Madrid Spanish, Mexico City Spanish.
It forces programmers to stop thinking about language families and start looking at language features. And that field is called typology.
This is where we group languages not by their history, but by how they actually work. Like a simple question, does this language use the word "the"?
Right. English has it. Spanish has it. Most Slavic languages, like Russian, don't. That's a huge structural difference for a computer to handle. Or think about cases. In Latin or Russian, the ending of a noun changes depending on if it's the subject or the object.
Whereas in English, we just rely on word order.
We do. And the source mentioned ergative languages, which is a total mind bender.
It really threw me.
It's a completely different way of seeing the world. In English, the subject does the action, I broke the window. In a lot of ergative systems, it's more like the action happens to the subject. The grammar marks it differently.
So if you're building a translation program and you don't account for that fundamental structural difference,
You flip the entire meaning of the sentence. You just produce nonsense. And all of this leads to the source's biggest warning. They call it the engineer's fallacy.
oh, I felt personally attacked by this part. This is the idea that, hey, I'm a really good programmer, I have a fast computer, I don't need to read some dusty linguistics textbook, I could just brute force this problem.
And the source is just brutal. They say, to their knowledge, every single major attempt to do that has failed. They use this wonderful physics analogy.
The laser technician.
Yes. Imagine a technician who only knows about lasers. They're an expert on that one device. But they don't know the fundamental laws of physics, of light and energy.
So if the laser breaks or someone hands them a flashlight, they're completely lost.
Exactly. But a true physicist, they understand the fundamental laws. They can look at any device, a laser, a light bulb, a star, and figure out how it works. And the source's argument is, don't be the laser tech, be the physicist. You need the fundamental linguistics, the theory, or your software will always be brittle.
And they point out that this is actually a looming crisis for the Spanish language specifically. I mean, we think of Spanish as this massive global language, over 400 million speakers.
But the research is incredibly Anglo-centric. Almost all the big NLP tools, the breakthroughs, they happen for English first. The tools for Spanish are just years behind.
Even with things like the Royal Academy Dictionary.
Dictionaries are for people. They give you definitions, feelings. Computers need algorithms. They need a formal mathematical description of how libro connects to libros. We have to build that linguistic stack for Spanish pretty much from the ground up. You can't just copy-paste the code from English.
The conclusion the source draws from all this is, it's pretty stark. It stops being about grammar checkers and becomes about cultural survival.
They call it the total information revolution. And the argument is really simple. In the 21st century, knowledge is everything. If your culture's language can't be processed by machines, if you can't search it, analyze it, translate it instantly, you fall out of the global technological conversation.
You essentially become invisible.
You become digitally illiterate as an entire culture. And so for a country to remain competitive, it's mandatory to teach machines how to read your language.
That's a heavy thought.
Yeah.
It's not just about getting Siri to set a timer anymore. It's about whether your culture even have a voice in the digital future.
It is.
So here's the thought I want to leave you with. The next time you use Google Translate or you ask an AI a question, I want you to think about all those layers. Think about Yuri Norizov's statistics running the background, just frantically counting word frequencies to fake a sense of understanding. And then ask yourself, is that machine actually communicating with you? Or is it just a very, very fast parrot that has memorized the entire dictionary but understands absolutely nothing about what it means to be human?
That is the question that keeps a lot of linguists up at night.
Thanks for listening to this deep dive into the machine that reads. We'll see you on the next one.